Hi, folks. Today we're going to talk about symbolic logic. And so, when we start talking about the idea of universal truths and what it means to be true and false, we really need to try to understand what certainty even means. So, recall our original definition of mathematics. Mathematics is the study of universal truths through the analysis of definitions and conditional statements. It's a subject which, at its core, focuses on an understanding of substance and structure and can be thought of as the study of absolute certainty. Up to this point, we have focused on a great many structures, but we have not yet discussed what it means to be true. And so, what is a universal truth? How do we get there from the definitions and conditional statements? How do we even define certainty? Well, in our last few lectures, we're going to start talking about what it means to measure uncertainty. We now understand what it means to measure things, but we still need to understand certainty and uncertainty. And that's where mathematics and philosophy start to meet up. And so, what is symbolic logic? Well, we know what logic is. Logic is ancient. Logic is the idea that we can put ideas together and have some form of deterministic outcome. It's an approach to understanding truth. And logic really is the underpinning of all of mathematics. And so the question then becomes, how do we formalize it? Well, there have been many, many attempts across the last few thousand years to try and formalize it. One of the biggest ones from the last few hundred years is symbolic logic. And it's a way of just breaking down statements into symbols and then being able to create arguments based on the structure of the arguments. And so let's see if we can understand all of this stuff. The structure of logic. And so let's begin with some definitions. A sentence is a collection of words, usually involving a noun, verb, and whatnot. Hopefully, we know what a sentence is. We consider a sentence to be a statement if it is something which could be considered either true or false, but not both at the same time. And so a statement is something which is either true or false, but not both. And a logical argument is a set of statements, which we call the premise, which are used to support another statement, which we call the conclusion. We use the therefore symbol, which is 3 dots, to denote when we've gotten to the conclusion. And so here's a simple example. Ice cream example. Adam has $20. An ice cream cone costs $4. Therefore, Adam has enough money to purchase an ice cream cone. All 3 of these sentences are statements because they could be true, they could be false. It forms an argument with 1 and 2 as the premise and 3 as the conclusion. And so now the question becomes, does the conclusion follow from the premise? It sure seems to, but let's see if we can try to understand what that would mean. And so deductive reasoning is an approach to arguments which strives for certainty. Given an argument, we say that it is deductively valid argument, or we would just say it's valid. If provided the premise is true, the conclusion must also be true. If it is a valid argument, then if the premise is true, it is impossible for the conclusion to be false. If it is possible for the premise to be true and the conclusion to be false, we say it is an invalid argument. And so here's our ice cream example again. Adam has $20, an ice cream cone costs $4, and Adam has enough money to purchase an ice cream cone. In this case, if the premise is true, then yeah, the conclusion would naturally follow for this. This would be a valid argument. If we only had 1 and 3, and so if we said Adam has $20, therefore Adam has enough money to purchase an ice cream cone, well, we couldn't be certain of that because we don't know how much an ice cream cone costs. If an ice cream cone costs $100 or something like that, then he wouldn't have enough. And so that's where we have to be very careful with how we phrase things. Inductive reasoning is not as useful in logic and is used much less in formal mathematics. We do see it occasionally in statistics and probability where we're dealing with uncertainty, but we don't really see it in math because it doesn't create a causal link. And so here's an example. Adam has enjoyed every ice cream cone he has ever eaten. Therefore, Adam will enjoy the next ice cream cone he eats. There is no guarantee of that. There is no causal link between there. Just because he has enjoyed every one that he's ever had doesn't mean the next one he's going to have will be any good. Maybe it has a bug in it or something. This is an example of an inductive argument. While the premise may support the conclusion, there is no certainty here. It is possible for the premise to be true and the conclusion to be false. Now let's start talking about different operators. And so when we think of binary operations from back in algebra, well, we have operators in logic as well. And so operators are a way of manipulating a statement or of combining different statements. Our first one will be and. And so if A and B are true, then that means that A is true and B is also true. And so that's what's meant by and. If either one of them is false, then the whole thing is false. And so our ice cream example, statement one is Adam has $20 and an ice cream cone costs $4. Therefore, Adam has $20. Well, that's true. In this case, Adam has $20 is one of the statements, and using and is combined with an ice cream cone costs $4. In this case, the argument is valid on its own and is not that impressive, but it's a good starting point. And so we'll need some more operators to do some more interesting things. For example, not and or. These are a couple more powerful ones. And so if A is true, then not A is false. If A is false, then not A is true. Not is an operator which just switches the truth. Our third operator will be or. And so suppose that A or B is true. Then if A is false, B must be true. If B is false, A must be true. But it's also possible that both things are true. If we know A or B is true and we know not A, then B must be true. And so we can start playing around with some of these ideas. Here's an example. Adam has $20 or Adam has an ice cream cone. Adam does not have $20. Therefore, Adam has an ice cream cone. There we go. And so this is an example of this statement that we had down here. If we know A or B is true and we know not A, then B must be true. In this case, A is Adam has $20 and B is Adam has an ice cream cone. This is a valid argument. The next one is an if-then statement, also known as a conditional statement. We've actually been using these for everything. When we say therefore, that is assuming that if the premise is true, then the conclusion is true. And so we know what if-then means, but let's see if we can formalize it a little bit. And so suppose that you are told if A, then B is a true statement. Well, if A is true, then B must be true. If A is false, then B could be true or it could be false. We cannot determine B. And so essentially, if we have a premise which is false, we can deduce nothing from the conclusion. And so here's an example. If Adam has $20, then he has enough money for ice cream. Adam has $20, therefore, Adam has enough money for ice cream. Here's an alternative version. If Adam has $20, then he has enough money for ice cream. Adam does not have $20. Well, we don't know if he's got enough money for ice cream then. And so Adam has enough money for ice cream, or maybe he does not have enough money for ice cream. We cannot really determine one way or the other. Ooh, our next one is the if operator, which has an extra F in there. The if operator stands for if and only if. It is known as the biconditional. And so this is a two-way if-then statement. And so statement A, if and only if B is true, means if A, then B, and if B, then A. So either both statements are true or both statements are false. It's impossible for one statement to be true and one statement to be false. We can even think of this as equating the two statements. Wonder if we could even form an equivalence relation. And so, ice cream example. Adam has $4 if and only if he has enough money for ice cream. Adam has enough money for ice cream, therefore Adam has $4. And so in this case, if Adam has the $4 or if Adam has enough money for ice cream, then the other statement is also true. If one is false, then the other must also be false. Similar to this is the exclusive or. And so the exclusive or, also represented as XOR, is a statement which is an or statement where only one of them is allowed to be true. And so if A XOR B is true, then if A is true, B is false. If B is true, A is false. They can never both be true or both be false. It's got to be one or the other. Note that this is the negation of the biconditional. And so we don't use this one as much, but it does come up every now and again. And so here's an example. Adam has $4 or he has an ice cream cone, but not both. Adam has $4. Therefore, Adam does not have an ice cream cone. In this case, one is an exclusive or statement. Since the first statement in the exclusive or is described as true, the second statement must be false. So now that we've introduced some of the operations, let's go back to what it means to be valid and introduce the idea of being sound. And so to be a valid argument, it means that if the premise is true, the conclusion must also be true. To be a sound argument, the argument must be valid and the premises must be true. So far, that's mostly what we've looked at, and this is what mathematics is built upon. It's built upon the idea of sound arguments. And so here's the ice cream example again. An ice cream cone is either a fruit or a vegetable. An ice cream cone is not a fruit. Therefore, an ice cream cone is a vegetable. In this case, the argument is valid because if the premises were true, the conclusion would be true. But it is not a sound argument because the first statement is not true. An ice cream cone is not either a vegetable or a fruit. And so in this case, it may be valid, but it is not a sound argument. Along with this idea, we have the idea of consistent. And so an argument is said to be consistent if it is possible for all of the statements to be true. Sometimes it's not possible. And if it's not possible for all of the statements to be true, we would say it is inconsistent. If it is inconsistent, then that means there is a contradiction of some form, meaning the logic is not sound. We often use contradictions to prove things. Essentially, assume a conclusion is false and then reach a contradiction, meaning it must have been true all along. And so here's an example. Ice cream. The ice cream cone is either vanilla or mint. The ice cream cone is either mint or vanilla or mint or chocolate. And then the third one is the ice cream cone is either chocolate or vanilla. We've reached a contradiction. Essentially, if we know that it's either vanilla or mint, well, that means that if it's also mint or chocolate, then it must be mint. But that doesn't work for this third one, because if it's mint, then it's not chocolate or vanilla. Another way to think of it, if we're saying that the ice cream is vanilla, well, then it's not mint or chocolate. If we're saying that the ice cream is mint, then it's not chocolate or vanilla. And so we can't have all three of these things be true at the same time. It's an inconsistent argument. So now that we've introduced some of these basics, let's explore truth. What does it mean to be true and false? And in order to do this, we're actually going to use some symbols. And so the reason we call this rudimentary form of logic symbolic logic is because we often simplify things using symbols. And so the table to the right shows some common symbols. There are many other symbols, but we'll be using this set. And so we have the negation. The negation is given by the tilde. We have a conjunction, which is and. So this is x and y. This one would be x or y. This is an if-then. Then we have if and only if. And then we have our exclusive or. And so let's see if we can play with these and understand what it means to be true or false given one of these propositions. And so here's our truth table. A truth table is a table which shows possible outcomes of a series of statements, dependent on whether the initial statements are true or false. For our 6 operators, note that they each have a slightly different truth table. In particular, pay attention to the conditional, as it's a little bit weird. And so let's go through these. Here we have A is true, true, false, false. And so A is either true or false. And B, we have true, false, true, false. When we notice this, when we look at A and B, they're either both true, one's true, one's false, one's true, or they're both false. And so this is showing all of the different possible things that can happen. And I've just copied that down here so that we can see the other one. And so let's look at not A first. And so if A is true, not A is false. If A is false, not A is true. That one's easy. A and B. And so if A and B are both true, then we get true. If A is true and B is false, then A and B would be false. And same with the other ones. Essentially, for A and B to be true, they both must be true. For A or B to be true, well, only one or the other needs to be true. If they're both false, we get false. But A or B is true if either one of them is true. And so the conditional one is the one which is tricky. And so A implies B, or if A, then B. If they are both true, well, then this is a true statement. If the first one is true and the second one is false, and so if we're saying that this is true and this is false, then the conclusion that if this, then this is a false statement. However, if we are starting with a false premise, then it's going to be true no matter what, because we can't determine that it's false. And so that one's kind of weird. This is like saying, if pigs can fly, then I'll run a marathon. While the premise is false, the statement as a whole is true regardless of the conclusion. We then have our if and only if, and so that would be true if everything's true or true if everything's false. And then our exclusive or, and so A exclusive or B. Well, this is only going to be true if one or the other is true. If they are both false, then it's no good. Cool. Let's keep going. And so when trying to understand a statement, we often combine different symbols. These are binary operations, so we use parentheses to signify the order of operations, just like we have in set theory and everything else. And so be careful. When we think of statements, small changes in the statement can make for different statements. In the example to the right, currently having $4 and future having $4 are different things and require separate statements. And so here's our ice cream example. If Adam has $4, then Adam will have either $4 or ice cream cone, but not both. And so in this case, statement A is Adam has $4. Statement B is Adam will have $4. And statement C is Adam will have an ice cream cone. And so in this case, we could say A is implying the exclusive or of B and C. And so if Adam has $4, then either he will have $4 or he will have ice cream, but not both. And so we can do truth tables with 3 statements. And so here's an example. In order to create a truth table with 3 statements, we would create a column for A, B, and C. And then we would just need to make sure that we are including every possible combination of those 3 statements. And so note, we go true, 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 false, 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 false. True, true, false, false, true, true, false, false. And then true, false, true, false, true, false, true, false. That's an easy way to represent all of the possible outcomes, because now we have all 3 are true, the first 2 are true, and the last one is false. The first one's true, the middle one's false, the last one's true. This is every possible outcome. And we can then create these truth tables. And so in this case, B exclusive or C. And so in order for B XOR C to be true, we would need one to be true and one to be false. Otherwise, it's going to be false. And so in the first case, they're both true, so this is false. For the next case, one's true, one's false, so we get a true statement. For the next one, false and true, that means it's true. Both false, it's false. And then we can repeat that. These next four are the exact same. False, true, true, false. We can then do the truth of A implying this thing that we just created. And so now we have, if this is true and this is true, then this statement is true. If this A is false, then this is automatically true. And so looking here, we have true and false, that's false. True and true, that's true. True and true, that's true. True and false, that leads to false. The remaining are all false as a premise, so they're automatically true. And so this is the truth table for the statements which we just did. And so if A, then B exclusive or C. And so we can work our way through this and determine when this is true and when this is false. And so now let's look at the example we have. If Adam has $4, then Adam will have either $4 or ice cream, but not both. Well, we just figured out when this is true and when this is false. And it looks like there are two different conditions where this is a false statement. One of them would be if Adam has $4 and then later has both $4 and an ice cream cone. And the other case would be if Adam has $4 and later has neither $4 or an ice cream cone. And so in using a truth table, we can figure out exactly what the cases are where something is going to be untrue. And so when is the argument not going to be sound? Tautologies are something we usually strive to get. And this is where we can talk about universal truths. And so as an example, to kind of guide the discussion, we'll talk about the contrapositive. And so the contrapositive is a way of going between a conditional statement and their negations. And so here's the example. If there is photosynthesis, then there is light. Because in order for photosynthesis to happen, you have to have light. And so if there's photosynthesis happening, there must be light. If there is no light, then there is no photosynthesis. These two statements are equivalent. And so if we wanted to create a truth table to show that these two statements are equivalent, we would start by saying, let's let A be, there is photosynthesis, and B be, there is light. Well, then our first statement is A implies B. If A, then B. Our second statement is if no B, then no A. So no B, then no A. If we are saying that these are equivalent, then we're saying this is true whenever this is true. And so that is an if, or a double if statement where this is true if and only if this is true. What would the truth table look like for this? Well, here it is. And so we start with our A and B. And so this has all four possibilities. And then we can say, well, A implies B would be this. Not B would be this. Not A would be this. Not B implies not A. Well, that would be this. And then we can get our final thing. And so A implies B if and only if not B implies not A. And we end up getting that all of these must be true. And so this is a tautology. A tautology is a statement which is true regardless of the statements involved. And so in this case, it does not matter if A or B are true statements or false statements. A implies B is exactly the same as the statement not B implies not A. And so it's always going to be true. If all possibilities are false, we would say that it is a contradiction. If there's a mixture of true and false, then we would say it's a contingency. Usually we are looking for tautologies or a contradiction. And so here's a practice or a set of practice problems. And so while there is more to logic than to tautologies, they give us a way to understand the idea of certainty. Here's an example to the right. And so if we have P, well, P is either true or false. Not P would be, well, false and then true because it's just the opposite of these. If we are talking about P or not P, well, that's always going to be true because one or the other must be true. If we're talking about P and not P, well, that will never be true. And so in that case, it's always going to be false. You might also notice there's this other symbol, which is sometimes used for not. And so here's a challenge for you if you are up for it. Here are a set of different statements. If you would like, you can try and pause the video and create a truth table for each one of these. Or if you'd like, just do one or two of them. And then we'll show you all the answers for these. And we'll see if we can go a little in depth into it. All right, let's go through them. So our first one is the biconditional. And so the biconditional, that is our if and only if. And this is a way we can define our if and only if. Note, usually it's a bad idea to define if and only if in terms of if and only if. You don't want to define things in terms of what you're just, or in terms of themselves. But in this case, it works fairly well. We can start with the idea of the biconditional being defined by the truth table, and then this gives us a new way of describing it. And so if we let A and B both be true, or one's true and one's false, or one's false and one's true, or they're both false, we end up getting a tautology out of this. What this is saying is A if and only if B means the exact same thing as if A then B and if B then A. And this is why it's the biconditional. It has to be conditional one way and it has to be conditional the other way. Ooh, our next one is modus tollens. And so let's see if we can understand this tautology. If A then B and not B, then not A. And so if we know this statement is true, if A implies B and we know that B is not true, then that means that A must not have been true to begin with. And so a way to think about this, if photosynthesis means there's sunlight and there's no sunlight, then that means that there's no photosynthesis. The law of syllogism. And so this is an important one in philosophy. If A implies B and B implies C, then A implies C. And so this is how we can string together if-then statements. This is how we can string together conditional statements. If we have a series of conditional statements, then all we need to do is start with that first one and we can kind of knock over that first domino and we can get all of the remaining conclusions. De Morgan's law is another big one. It's a way of dealing with negations. And so this one is saying, suppose you have A or B. Well, let's go with not A or B. If it's not A or B, then that means that it's not A and it's not B. If it's not A and B, then that means that it's not A or it's not B. Essentially, if one of them is not true, then the statement of both of them being true is wrong. Additional tautologies, there's a lot of them. There's a whole lot of tautologies. While truth tables can help us understand the consequences of true and false statements, tautologies are always true. And so no matter what statements you put into these things, it is always going to be true. And so here's the question. Can all of math be broken down into a set of tautologies? And this was a very big question for a very long time. And that leads us to the idea of the Principia Mathematica and Gödel. And so let's talk about axioms again, because they just keep coming up. That Euclid had some good ideas. And so Euclid defined geometry in terms of 5 axioms. And so general premises, which we could assume true. How do we know that those 5 axioms are consistent? How do we know that those 5 axioms aren't redundant? What if we only needed 3 or 4 of them? Well, how would we even know? These were open math questions into the 1800s when Gauss and a number of others determined that the axioms of geometry are consistent. But what about other fields? How do we determine if there's not some horrible paradox that we aren't even aware of? And that makes things challenging. In particular, because of the principle of explosion. And so why do we need our premises to be consistent anyways? Well, it turns out if 2 axioms are contradictory, logically, we can prove anything to be true. And this is called the principle of explosion. And we can prove this without too much trouble. And so if both P and not P are true, and then let Q be any statement, whatever you want it to be, well, P or Q is necessarily true because P is automatically true. And we also know that this is a tautology. And so P or Q and not P, then Q. This was one of the tautologies we just talked about. Well, in this case, our premise is true. And so our conclusion must also be true, which means no matter what you say, it's automatically true. And so we cannot have inconsistent or contradictory axioms. That ends up breaking math in horrible, horrible ways. And one example is Russell's paradox. We used to have set theory where it was just kind of a general idea of we can put whatever we want in sets and there was no rhyme or reason to it. And this ended up leading to some horrible, horrible paradoxes. And one of the big ones is Russell's paradox. And so by the late 1800s, there were weak spots starting to form in the foundations of math. And we've already seen paradoxes like Zeno's paradoxes from Greek. Zeno's paradoxes showed that there were some weak spots in Euclid's geometry. There were things that were missing. We needed additional tools. And that's where Descartes came in and said, well, what if we thought about geometry from an analytic geometry perspective? And once we had that, we were able to define things like motion and give structure to motion, and we got all of calculus out of it, and all of Zeno's paradoxes cleaned themselves up really quick. And so Russell came up with a paradox which turned set theory on its head. And here it is. Let set R be the collection of all sets which do not include themselves as members. And so this is kind of a weird thing to think about. And so suppose that you've got S, which is a set, which is 0 and S. And so it actually includes itself in the set. And so that means that S contains itself. According to this definition, R is the collection of all sets which do not include themselves. That would mean that S is not in this set. Well, the paradox is R included in itself, or is R not included in itself? To try to understand the intent, Russell came up with a different version of it involving a barber. You may have heard of the barber's paradox. This comes from Russell. And so let's think of this statement. The barber is the one who shaves all those and only those who do not shave themselves. Who shaves the barber? And so in this analogy, if the barber shaves himself, then he violates the rule of shaving only those who do not shave themselves. If the barber doesn't shave himself, then he violates the rule of shaving all those who do not shave themselves. And so in this case, the barber must shave himself, but he's also not allowed to shave himself. That's kind of a problem. And so how do we deal with that? Well, this was a big issue, a huge issue. And so a bunch of philosophers, Alfred North Whitehead and Bertrand Russell, they tried to create logical foundations for math which would not have this issue. And they wrote this set of books titled the Principia Mathematica, which was designed to be a logical foundation for all of mathematics. With how mathematics had broadened the last few hundred years, it was an attempt to answer the question of what is mathematics? How do we define it? Well, they tried. And so the goals of the Principia Mathematics were threefold. Try to create a structure to describe all of mathematics using the fewest number of axioms. And then two, create a symbolic logic notation that can describe all things in mathematics. And the last one, clean up the many paradoxes which were hiding in mathematics, particularly in set theory and logic. They did their best. That's about all we can say. And so let's talk about the good and the bad of the Principia Mathematica, this work that they spent decades working on. In identifying the issues of modern math, mathematicians worked to resolve the issues and build cleaner structures. And so that was something they did right. They said there is an issue here. And other mathematicians cleaned up the issue. The Zermelo-Fraenkel set theory that we use today, all of the set theory stuff that everything we have done in this entire lecture series is built upon, it came out of this. And so this is something from the last 150 years or so. And the idea of formalizing mathematics and logic was a good one, which inspired many people. And a lot of people have tried to formalize things. The Bourbaki group, for instance, they said, what if we each just took one big branch of math and tried to formalize it? And there was a lot of good stuff that came out of that. That said, the Principia was dense, its symbols were unpolished, and there were some very big issues. One half-true joke is that it needed 360 pages to prove that 1 + 1 is equal to 2. And it's true. They actually have the proof. 1 + 1 = 2 on page 360. That's not great. I mean, hopefully we would reach that sooner than that, but maybe not. I mean, in breaking things down into the fundamental principles, the ideas of addition didn't come until much later in the texts. When we started talking about addition in this lecture series, we didn't really get there until we started talking about binary operations of algebra. And so there was a lot of other stuff, a lot of other structures, which we explored before we got into this idea of binary operations. It also wasn't great at formalizing, which was a problem because that was one of the main points of it. And so all of their symbols were not great, and mathematicians later had to redo all of them. Worse, Gödel came along, and Gödel just threw a wrench in the whole system. He changed the way that we view mathematics. And let's talk about how that happened. And so in the late 1920s, Kurt Gödel, as a mathematician and logician, was a critic of the Principia, and he developed a powerful proof. He proved that under any set of axioms, there will always be true things which cannot be proven by their axioms. Moreover, any set of axioms could not prove themselves consistent. These became known as the incompleteness theorems. This challenged the idea of developing an axiomatic approach to all of math, which is what they were trying to do with the Principia. Basically, it's not possible. We cannot create a set of axioms that describe everything. There will always be things that we can't prove. And there were also much greater philosophical ramifications. There are unknowable, unprovable truths about reality. And this is the truth of the universe. As mathematicians, we must be okay with this. We must be okay with the idea of there being things which, no matter what axioms we use, we will not be able to prove them. And so in a field which is focused on discovering truth, this really changed how we viewed what is true and what is not. And so when we think of modern proofs, we don't often go back to the truth tables. We know the truth tables are there. They're great, and we can always go back to them if we need to. But for the most part, we don't. Instead, we're using the idea of premise and conclusion. And so our premise involves whatever set of axioms, domains, and definitions are in play. And usually in different fields of math, we will say, oh, we're dealing with geometric objects. We're going to use the axioms of geometry. Or we're dealing with set theory or topology. Well, we're going to use the axioms of set theory. The axioms of set theory really underlie the majority of what we are dealing with. But the conclusions must then be deductively true based on those premises. And so here's an example. All prime numbers greater than 2 are odd. Every single word in that statement carries with it important definitions. What do we mean by all? What is a prime number? What's a number? What does it mean to be greater than? What is 2? What does it mean to be odd? What does the word are mean? Every single one of those has a mathematical definition. And we accept those mathematical definitions as we are trying to prove things. And so in using deductive reasoning, we take symbolic logic to a higher level language to demonstrate the truth of a statement. One of the common ways of viewing this is similar to how computers work. And so when you think of computers, they're based on a binary language of ones and zeros, unless you're talking about quantum computers. And that's really just what a transistor is. A transistor is either something which is powered or unpowered and represents true or false. Well, we have a compiler which is able to then turn that into object code, and then we're able to, or sorry, I'm going the other way around. We have something which links object code to the binary language, and then we have a higher level language which is able to link to those object codes. And so programmers don't often play with ones and zeros. Instead, they're using some programming language like C++ or Java. And using that higher level language, they're able to get computers to do what they want them to do. That's similar to what we're doing in math. When we are exploring proofs, what we're really doing is we're using common language in order to manipulate these truth tables, but we don't typically focus on the truth tables themselves. Final thoughts. Mathematics at its core is the study of certainty, and the ideas of logic and deductive reasoning are the foundation. All of math uses this as the underpinning. Without logic, we have nothing. While there have been issues in formalizing it, those issues have led to some amazing results. The incompleteness theorem, for instance, it revolutionized how we think about mathematics. These ideas of logic and this philosophy of unknowable truths applies to far more than mathematical structures. We all strive to do what is best, and we often want best to be a logically defined best. But how do we determine what is best from a moral perspective? Well, we can use mathematics to try and determine what is moral in certain situations. But then comes the question, can we use mathematics to lie? And this is kind of leading to the idea of probability and statistics, as well as a little bit more with logic. When we're thinking about probability, we are trying to measure uncertainty. And that means that we have to know how to measure things, and we have to know what it means to be certain or uncertain. And that's really all of this logic stuff. Statistics, well, statistics is going to give us some tools to tell stories. And those stories could be true and those stories could be false, but we can tell whatever stories we want, and then it's up to the reader to determine if those stories are true. But as the reader, we must also try and figure out when we are being told a truth or a fallacy. And so understanding statistics deeply is going to be very important in understanding truth and lies. With that, I'll let you get to work exploring where you find logic in the real world. Good luck, folks.